Okay, good morning. Let me start the lecture with a few administrative stuffs. The first one relates to the scheduling for the next weeks. As you can see here, I posted this update on Portale Didattica. I already prepared a number of seminars given by companies to you, because I'm convinced that it is important for you to have a look to what is waiting for you outside Politecnico. So we will have a lecture today. I am giving you the introduction to AUTOSAR. This is basically the last theoretical part that I am covering in this class. Then from the next lecture, besides the seminar that we will have, I will start doing exam examples. This is in preparation for the final exam to give you the chance of making some practice and to recap a little bit what we saw about ISO 26262. This is because remember that the written part of the exam will be based on the first part of the class, that is ISO 26262. So you will have to analyze items and do all the steps of the concept phase as we have seen together in lectures. Then besides this theoretical part, as I said, I have prepared a number of seminars from experts. So on Friday, we will have a person coming from this space that is is a company located in Paderborn. So he's coming right here in Torino for us, traveling for us, to give a seminar on the virtual validation. This is a new methodology that is becoming adopted by companies. Many companies are not yet there, but in the next future they will use this approach. So I thought it is important for you to have a glimpse of this advanced technique. Then the coming week, there will be no lecture on Wednesday because I am on a business trip. We will have on Friday a seminar from experts of Fiat Chrysler automobiles. Well, this is an interesting opportunity to hear how model-based design is used in this company that is next door. So it could also be an interesting opportunity to meet possible contacts for thesis or maybe job offers. Then we will have a seminar on Wednesday the 1st, given by a company that is one of the founders of many initiatives related to coding style for safety and developers of a tool for static analysis. They are coming from UK to visiting us to give this talk, so it is important to recognize their effort. And we will have a talk about static code analysis for ISO 26262. Then we will have, well, this is yet to be defined. In principle, I'm expecting to have the last day of the class a meeting with a company that is presenting as Modelica. This is an expert coming from Sweden. Modelica is a tool that is being adopted in many companies for modeling complex mechatronic systems. So this is to give you a view about what is used in the industry besides MATLAB and Simulink. You may see that there are two slots where we do not have lectures. The first one is the 25th that I already told you, and then the other one is the June the 3rd. This is because June the 2nd is national holiday. June the 3rd is Friday, so I thought it was good to have a long weekend here. Obviously, we don't have to miss the lectures, so I scheduled 2 additional lectures devoted to exams. These are planned for May 21st and June the 7th. They are on Tuesday afternoon. I checked on Portale Didattica, and it seems to me that mechatronics students are free on that slot, so I thought this is possible. There is an issue with the students from computer engineering, I know, but remember that we record everything and we'll set everything available on Portale Didattica. So I hope this is not a big annoyance for you, okay? If you have problems with this, let me know. We will try to arrange different time slots. But I really look into the Portata Didattica for the timetable, and it seems to me that for the computer engineering students, there is no option available because you have a very dense scheduling. And then this optional for you is eligible. So the scheduling has been set so to not to guarantee lack of overlapping. For the mechatronics students, I saw that you are free, so in principle it should work. If not, let me know, we can find a different agreement. Well, then the second issue that I want to mention is about the assignment. I think that most of you are already working on the assignment. Some of you are sending me emails, I will reply. In general, if you have doubts, feel free to write me, I will reply, and then if we don't solve the issue through email, we can meet, okay? Remember that you have time till the end of July to deliver the work. You have seen that the work is structured in function of the number of team members, so I think it is a fair allocation of tasks. Any doubt questions so far? Yes, please. Yeah, right. So we have May 21st, we will be in 3P, while June the 7th, we will be in 7D. Okay. Well, there is no setup for the recording there like the one that we have in this class. I will manage the recording through my laptop with Camtasia and set the files available to you via Dropbox. I already did this in the past semester for another class, and it is working. So you will have the recording of the voice and the slides. There will be no picture of myself speaking as you have in this with this setup, but well, this is something that you can miss. Okay. Any other question? Okay. So let's go. Oh, sorry. Let's switch to the content of the lecture for today. As I said, today I want to introduce you to AUTOSAR. So we will see why there has been the need for such a thing that is AUTOSAR. That stands for Automotive Open Software Architecture. And then we will talk a little bit about the key elements of AUTOSAR as well as the AUTOSAR methodology. What is important here for me is to give you let me say, a way for understanding what AUTOSAR is. You will not have time to gain a working knowledge of these concepts. It's not important. What is relevant is that you understand why AUTOSAR is here, why it has been defined, how it has been adopted, and which are the key elements. So AUTOSAR is an acronym that stands for Automotive Open System Architecture. This is an open architecture, that is a document that describes how software for electronic control units for vehicles should look like. So here you don't have a specific solution for a specific problem, like how to manage the power window, how to manage the steering, how to manage the braking. These are specific functionalities that has to be designed. So the idea of AUTOSAR is to give you a structured way for organizing the software that will implement the specific functionality. The consortium was founded not so many years ago, in 2003, by basically the big German car players. We have BMW, Daimler Chrysler, then that are the OEM, that is the company that builds vehicles. Then we have Bosch Continental and Siemens VDO. Those are the companies that build electrical parts and electromechanical parts for vehicles. And then also we have Volkswagen, another big OEM. Later on, this group of people was enriched by other OEMs and other tier ones that recognize the value of AUTOSAR. This is a more or less updated picture of the different companies that are part of AUTOSAR. We have the founding members, the core members, and then we have a number of associated members that decided to join the consortium that is responsible for defining the architecture. So you have to bear in mind that this is an architecture. So there is a number of documents that specifies how the different elements of this architecture should look like. The different ingredients are the actual structure of the software in the vehicle, the application programming interface that the programmers can use when writing software that is hosted by that architecture, and the methodology that designer must use in order to develop software consistently with the AUTOSAR architecture. As you can see here, there are many players that are working in this scenario. Obviously, we have the OEMs. These are the ones that are interested in allocating vehicle functionalities to software components. So they want to have the capability of describing what the software shall do. They are not interested in coding the software. This is something that somebody else will do. So they are interested in specifying what the software shall do. Then we have the tier ones. These are the supplier of electromechanical parts to the OEMs. And they are interested in understanding what OEMs want in terms of intended functionality. And they are intended to deliver these functionalities in the form of ECUs with embedded software running on top of it. So the two needs to speak the same language. OEM shall say what they want. Tier one shall be able to understand what the OEM wants and deliver exactly what is wanted. The other interesting part of this story is that if everybody agrees on the same language and being OEMs almost doing the same vehicles with the same requirements, the tier ones can be provide the same functionality to the implementation of the same functionality to multiple OEMs. This is because all the OEMs speak the same language. Similarly, the OEM having the capability of using a well-established standard for describing what it wants, it can make the question to plenty of tier ones for the support of a given functionality at the best price. So it is a win-win solution. The OEM can talk with multiple vendors. The tier ones can offer their services to multiple OEMs. This is solving a big issue that were affecting the automotive industry more or less 10 to 15 years ago. That was related to the fact that OEMs normally were using always the same tier one for delivering, for the implementation of the needed functionalities. And tier one was serving only one client, basically one big OEMs. This was a kind of rigid market. If one tier one has a problem, the OEM that historically always used that tier one has problem too. Similarly, if the OEM that is giving work to a given tier one runs into problem, the tier ones also has problems. With standardization, so that everybody speaks the same language, there is a much more flexible market. So the tier ones can offer the same services to multiple OEMs, and the OEMs can have the services from many different tier ones. Then, as you can see here, we have a number of other players. We have standard software, tool and services, and semiconductors. This is because with the standardization of the software architecture, we had that some of the software components running on the electronic control unit can be standardized as well. 15 years ago, when an OEM needs to have an ECU, it was up to the selected tier 1 to implement everything. The hardware and all the software running on that hardware, starting from the basic services, the operating system, the application. With the AUTOSAR approach, this is no longer needed. Being the different elements of the software architecture standard, you can have software vendors that provides you pieces of this software stack. The very same way you can go on the market and buy, for example, an operating system. It is the same example. There is a standardization of components. So your ECU can be built from pieces of software that are coming off the shelf. Typical example is the operating system. We spent quite a good amount of time talking about the configuration of the Simulink solver so that we can generate code that fits nicely in a process model where you have multiple tasks running concurrently, each implementing the step function. Okay. Well, this is to say that this implies that in our electronic control unit, we need to have an operating system. So 15 years ago, all the operating systems for ECUs were custom made. For example, there is CRF that developed an operating system that is called RTK, that stands for real-time kernel, that was used in all the electronic control units for engine and gearbox management in the past 15, 20 years. Well, with AUTOSAR, the scenario totally changed. Today we have vendors that supplies operating system for automotive application. They could be coming from big players like ETAS, DSpace. We could have something that is open source. There is an open source operating system for automotive applications that is called Erica Enterprise. So on the landscape, we had new players coming. Where is the value there? Well, basically, if you can develop standard components, well, first you are able to sell to much more clients because there will be more companies with the same need that you can solve. And then you can have flexibility. Today you can use the software solution from Vector, tomorrow you can use the software solution for ETAS. In principle, without any extra cost. In practice, with some extra cost, but it is still manageable. Then we will see that the methodology behind AUTOSAR requires a lot of automation, and for this you need tools. That's why we have companies that are providing tools and services that are customizations of the tools that joined AUTOSAR. Last but not least, we have the semiconductors vendor. Obviously, if you are a semiconductor vendor and you want to play in the automotive field, you need to be aware of what is happening in the automotive industry, especially if you are building microcontrollers that will run AUTOSAR software. So that, for example, you can implement specific features in your silicon that could support the best execution of the AUTOSAR software. And that's why semiconductors players are here. So why we need AUTOSAR? Well, it's clear from this picture. 20 years ago, the complexity of the control units and the number of the control units were quite low, so it was manageable basically with any in-house approach. Today is no longer the case. The number of ECU grown significantly, the complexity grown exponentially. The need for having the capability of using commercial off-the-shelf components is crucial to keep the cost, the development cost low. So that's why the industry decided to find an agreement in this architecture. So the main drivers for AUTOSAR were the management of the complexity of the electrical and electronic part of vehicles. Then there was a need for more flexibility in the modification, upgrade, and update of our software. So we need to be able to extend the functionalities easily and to change a portion of the components of this software much easily than what was possible before. Then there is also the need for scalability. We will see this later on, but let's imagine that you have a certain nice application, and then you want to deploy this application in one vehicle using one ECU. In another vehicle, you want to deploy the same application using 2 ECUs. This is because the OEM gave you some constraints. So if we have a way for easily mapping the same application on different hardware architectures, then we can do our job with very low cost. Conversely, if we have to make significant modifications to our software to make it able to run on different hardware platforms, we will have troubles to manage the requirements from our customers. And then also, obviously, there is always the need for improved quality and reliability. Remember what we saw in the past lecture when we spoke about software testing. Software quality is crucial because our software will make the difference between an accident or not. So obviously, any new technology shall support in an efficient way quality and reliability. What's the main concept behind AUTOSAR? Well, this is something that we already have seen in this class, but here it was the first time that this concept was conveyed in a structured form. The idea is to define the software running on top of an electronic control unit as composed of 2 big elements. The first element is the application, what the ECU shall do. That is the code for which your clients are willing to pay. And then you have an infrastructure that is whatever is needed to run the application. The 2 are independent. Well, this seems trivial, but it has a very big implication. If we adopt a well-defined interface between the application and the infrastructure, well, we can change the way in which we work. This is because being the interface between application and infrastructure well-defined and well-established, and everybody has to stick on that interface. This means that the application can talk to the interface, to the infrastructure, only through that interface. And the interface shall implement all the services that are foreseen by the definition of the interface. Then we can develop independently application and infrastructure. This means that our application can be deployed on many different infrastructures, provided that they all implement the same interface. What is the value here? The value is that we can decouple the development of the application from the development of the infrastructure. You can be a company that is very good on making the control algorithm to implement the vehicle stability. So you can develop an application for controlling the stability of a vehicle. And then you can deploy that application on an infrastructure that is coming from supplier 1, from supplier 2, from supplier 3. So this is a big advantage. You can deploy your asset on multiple products. So you have a greater market for you. Similarly, when you deploy a new electronic control unit, provided that it is implementing the interface foreseen by the standard, well, you can sell this to multiple markets. You can sell the ECU for the engine, for the chassis, for the, let's say, the air conditioning, and so on and so forth. You can address larger markets. So this is a big value. There is also another big value because sometimes OEMs develops their own application that they don't want to share with the tier 1 making the infrastructure. So the tier 1 can be responsible for delivering just the, let's say, the infrastructure that is, let me say, a dumb part of the ECU, and the OEM retains the intellectual property related to the application in-house. Think about a company like Ferrari. Ferrari that makes very impressive sport cars. Probably they have some specific algorithms, like the algorithms for controlling the engine, that they don't want to share with other companies. They want to keep this in-house. But they don't want to have the burden of implementing the electronic components for the electronic control unit that runs their algorithm. So once they negotiate the interface with the supplier, then they can go on the market and ask to whatever supplier, which is the discount that you give me on these 599 pieces that will allow you to say that your device is running on a Ferrari car. This is a very important way for negotiating and getting the best discount. And they can do this with any supplier capable of implementing something compatible with the standard. This is a very important element. So let's delve into the architecture so to have an idea of how this concept has been implemented. Well, here is the picture that is very similar to what we have seen in class already. If you remember what we spoke about the reference architecture for our software, we had the hardware, then we have the platform software, and then we had the application. Okay. Well, here is the same concept, but slightly more refined. So according to the software architecture proposed by AUTOSAR developers, the software on top of an electronic control unit shall be divided in multiple layers. Roughly speaking, the layers that you have closer to the hardware are intended for abstracting part of the services provided by the hardware. And those services are used by the upper layer for implementing other abstractions. Up to the, let me say, the red box here, we have what is called basic software. So the service layer, the ECU abstraction layer, the microcontroller abstraction layer, the complex device drivers are considered basic software. The basic software is basically common to any AUTOSAR ECU. So if you are developing basic software, you can sell this to those that build engine control unit, to those that build gearbox control unit, to those that build steering lock, and so on and so forth. So this is basic software, and it is common to all ECUs. Then we have the application layer, that is the layer where you implement your custom functionality. So if you are doing engine control unit, the application layer will be able to deal with 4 or 6 cylinder engines using standard services of the basic software. If you are doing a gearbox control unit, let's say automatic gearbox control unit, the application layer here will be, for example, implementing the control of a dual clutch system using standard basic services. Well, the glue that makes possible to run the specific application on the, let's say, general purpose basic software is this AUTOSAR runtime environment. We will see later on today what's the purpose of this. For the moment, let me just say that this is the thin software layer that takes the specific needs of the application layer and maps those needs on the standard services provided by the basic software. Okay? So now let's have a look at the different elements that we have inside this software stack. So right on top of the microcontroller, we have the microcontroller abstraction layer. When you write software, you don't want to know all the single details of your microcontroller. You don't care how a specific resource is programmed, like, for example, the GPIOs, the E2C, the analog to digital converter. You don't care how the specific function has to be programmed in order to get an interrupt when we have a rising edge on a certain GPIO. These are things that you want to avoid to know, because they are too complex, they are too error prone, and they are making you wasting a lot of time. It's like using embed. Now you have a bit of experience on embed. You have seen that with embed, you have an abstraction of the hardware. If you want to have a GPIO, just declare a suitable object of the specific type. If you want to have an interrupt, just attach a method to the specific edge of the interrupt you are interested in. So this is the job of the microcontroller abstraction layer, is to define an abstraction of the underlying hardware so that programming is easier. What is this abstraction? Is a set of libraries, let me call, or functions that could give you an easier access to the resources provided by the microcontroller. Well, this has a big advantage. The interface that the microcontroller abstraction layer exposes to the upper layers is always the same, while the code of the microcontroller abstraction layer is specific of the specific microcontroller, because basically this layer is implementing the interface for the specific microcontroller. So let's say we want to program a certain GPIO with a certain direction. Well, for an NXP microcontroller, you will have to write a specific code that will be different from the code that you will have to write for, let's say, NEC microcontroller. But the service that is provided, the set GPIO direction, is always the same, no matter which is the underlying hardware. So what's the advantage here? Well, basically, the silicon vendor can implement their own microcontroller abstraction layer that is compatible with any other component coming from software vendor implementing the upper layers of the basic software. So basically, the silicon vendor has the capability of serving multiple clients doing the work on their specific microcontrollers. And then this is also an advantage because the silicon vendor are the ones with the best knowledge of the silicon because they are designing it. So it is very reasonable that they are in charge of implementing this abstraction layer. And those that makes use of those abstraction layer have, let me say, good confidence in the fact that the silicon vendors did their own job. So they implemented the functions in the proper way. Then the same microcontroller can be used in many different ECUs. You can have an ECU for 4 cylinders, you can have another ECU for 6 cylinders, you can have another ECU for 12 cylinders, all running the same microcontroller. So when you develop the basic software for the specific ECU, you could have to provide different implementations of the defined services that is ECU specific. So I want to drive a current on the actuator 0, 1, 2, 3, 4, whatever. So at the upper level, I just want to have available the function set output current with a proper argument. Then it is up to the basic software to control the proper microcontroller abstraction layer in order to implement that command. So the ECU abstraction layer is intended for delivering to the upper layer the ECU specific services. Again, multiple makers can implement the same service in multiple different ways. From the application point of view, you don't care. You just want to have the services that you are expecting at this interface. Then we have a general service layer that is the topmost part of this that basically implements the operating system, that implements the memory services, the diagnostic services. So all those services that are, I would say, mostly hardware agnostic, that provides high-level functionalities like being able to store in a non-volatile memory the last few seconds of activity of the ECU in a circular buffer, or to provide the capability of scheduling the tasks of the application with a certain policy. These are very high-level services that are provided to the application developer. Then we have the AUTOSAR runtime environment. This is, as I was saying, the glue between the application on top and the basic software on the bottom. We will see this in more detail in a minute. On top of this, we have the application layer. And then here, we haven't commented this. This is the complex device driver. It's part of the basic software. This is a bit aside from the rest of the basic software. This is because this part here is the place where to encapsulate everything that cannot be standardized. This is typically, let's say, a backdoor for allowing developer of electronic control unit to reuse already existing software. The idea is to define on top of this very coarse interface so that the existing code, the legacy code, can be wrapped and used as is without the need for decomposing it in the different elements that are foreseen by the AUTOSAR architecture. This is, on the one hand, is a shortcut to reuse the code that you already have. On the other side, is not so efficient in terms of architecture based on components, because you have a monolithic piece of code that does everything. So it's very difficult to exploit the different layers, for example, to make modification in the ECU abstraction layer without the need for changing anything else. Well, here I give you a more detailed picture of the different layers that you have. You can see here that the microcontroller abstraction layer can be further divided in microcontroller drivers, memory drivers, communication drivers, I/O drivers. These are the pieces of code that implement the abstraction on the microcontroller hardware. Then we have services built on top of these drivers that are ECU specific. Then we have the general services implemented here. Besides this, we have the complex device driver and then the RTE and the application layer. Well, this is to give you a very broad overview of AUTOSAR. So, which could be your work in the automotive business related to AUTOSAR? Well, the first work could be application developer. So you will be responsible for modeling or for coding portions of this application that we will see in a minute are called software components. Once you are a bit more experienced, you will maybe you will be in charge of defining the architecture of this application, so deciding how many components you need to have, how they should communicate, and so on and so forth. And then somebody will be responsible for implementing the single components. Another possible job is to take the specification of the application and configure the runtime environment, defining how many software components you have, how they are scheduled, how they communicate, and so on and so forth, in order to generate the runtime environment for the specific application and to build this, assembling this with the basic software. Well, if you are working in an OEM, it is very likely that you will work at these two levels. So either at the application layer or at the software configuration layer. If you are working with tier 1 like AUTOSAR or Bosch or, no, not AUTOSAR, like Bosch, like tier W, it is very likely that you will be either in charge of the configuration of the runtime environment, or in case you are providing also engineering services in the implementation of portions of the application. If you are working with a company like AUTOSAR, DSpace, Vector, Electrobit, you could be in charge of building some portion of code here at the upper layers of the basic software, like for example working on the operating system, or working for customizing the ECU abstraction layer for the specific product that the specific tier 1, like Bosch for example, is building for a certain client project, like for example the new electronic control unit for CNH Industrial. If you are working with a semiconductor vendor like NXP, ST, Infineon, the many that are on the market, you can be in charge of working on the microcontroller abstraction layers. So there are multiple jobs for the different competencies that you may have developed here at Politecnico. Now, let's move to the AUTOSAR approach. So let me give you the big picture. The big picture is here. The application developers works at a very abstract level, that is the topmost part of this picture. So basically, your application will be implemented as a number of components that interacts. So the functionality that you have to implement for a number of reasons, like the simplification of the single components to enforce low complexity, the need for develop your application in a team that requires dividing the job among multiple designers, the need for using off-the-shelf software components that are already developing some of the work that you need to do, forces you to work in such a way that your application is divided in multiple components. Those components interact. Those components implement a specific functionality. So the single specific functionality is conveyed in the software component, the AUTOSAR software component. The AUTOSAR software component contains a specific behavior and interacts with other software components through specific, let me say, communication channels. These are port and port interface. We will see later on. Your application is made connecting the different software components. The set of communication channels that your application makes use of is known as a virtual functional bus. So what is important here is that when thinking about the application, you don't care about the infrastructure. So the application is developed independently from the execution platform, independently from the infrastructure that will take care of running that application. So when starting designing, you think in terms of which is the plan that you have to control, which is the best controller that you have to develop. You have to think how the controller should be mapped in software, partitioning the software in software components and making them interacting properly. So you reason in terms of software architecture. You don't care about the execution platform. Then, when you are happy with the definition of the application that you implemented, you can deploy this application on execution platforms. Well, here we have a lot of flexibility coming out from the AUTOSAR approach. This is because the deployment of the application on the execution platform, on the infrastructure, is done automatically, starting from some system constraints that the designer provides to the deployment tools. Let me give you an example. Let's imagine that for the specific functionality that we have implemented in this architecture, a certain OEM tells you that you must deploy them on 3 different electronic control units, this one, and that one. And according to the resources available on these electronic control units, you decide that the first software component shall go on the first ECU. Then the second and the third should go on the second ECU, and then the last software component shall go on this ECU. Okay? And then, due to the architecture of the vehicle, you have that these 2 ECUs are connected through a certain bus. Then we have a gateway, and the gateway enables the communication with these other ECUs. So, when defining the architecture of the implementation of the execution platform, you specified the mapping between software component and ECU. There is a specific language to make this mapping. Then, and these are the system constraints description. Then you define for each ECU which are the characteristics of the ECU, how many memory you have, which are the communication channels you have available, and so on and so forth. The deployment tool is responsible for configuring automatically the different runtime environments that shall run on the different ECU. Why is that? Well, let's imagine that ECU1 running software component 1 shall communicate through a proper channel with the ECU hosting software component 2 and 3. So it is possible that the virtual functional bus line that you see here on top, linking software component 1 with software component 2, needs to be implemented through network communication, let's say through messages over the CAN network of the vehicle. As application developer, you don't care about this detail. You care about the fact that software component 1 wants to communicate with software component 2. You don't want to change your application to make it able to communicate through CAN network. This is a standard service provided to you by AUTOSAR. So the deployment tool does its magic and define the RTE running on ECU1 in such a way that when software component 1 sends a message to software component 2, this message is translated into a CAN frame that is transmitted over the CAN bus. And it is received by the other ECU that makes the proper operation to notify the received data to the software component 2. Similarly, you may have the need for making a communication between software component 2 and 3, because you have some exchange of data among these two. So as the mapping is implemented by making the two software components stay on the same ECU, the RTE that enables the communication between the two will be different. You don't need to go on the CAN bus when sending data between these two software components. This is because they stay on the same hardware. So it is very likely that the RTE will implement this communication through shared memory, for example. Okay? Then, let's imagine that you successfully deploy this architecture on this software component, on this infrastructure. Then let's imagine that we have another client that is saying, look, I don't want to deploy your application on 3 different ECUs. I will provide you a very powerful ECU where you can map everything on this single ECU. So for you as application developer, you don't have to change anything. There will be a different system constraints description, there will be a different ECU description, and then the deployment tool will take care of making the communication possible between software component 1 and 2 happening through the suitable mechanism, taking into consideration that everything will be mapped on the same ECU. So here you can see the advantage of the flexibility offered by AUTOSAR. Once the application is fixed, so you are happy with the architecture that you built, you coded and tested everything, and then you are happy with what you have, deploying the same application on different hardware is in principle totally automated. So you can serve multiple requirements coming from possible different vendors. Or maybe you can make more flexible your internal products. Think about GM. GM here in Europe, they design electronic control unit, they design algorithms for controlling diesel engines. And they support multiple engines. They have the ones running in Europe that are 4 cylinders. Then there are the others in the US, there are 6 or 8 cylinders. So the infrastructure to run that application is different between the different continents. But the application is the same. So if you have an AUTOSAR architecture, you can easily map the same application controlling the diesel engine on different infrastructures specific of different applications. Similarly, here in Europe they design diesel engine, in the US they design gasoline engine, but the two shares some components. So if you have an AUTOSAR architecture, it is quite easy to put together the needed components. So to configure your application for the specific needs of a specific engine. If you don't have this possibility, well, it's quite more complex to manage design variations. So AUTOSAR is not just something that allows you to pay less for the hardware given to you by your supplier. It is something that could also be used for managing the complexity of the different product variants that there are inside the company. Then, having said this, let's move forward and let's have a look at the AUTOSAR software components closely. So the software components are the atomic unit of your design. So when you define an application, it is made of multiple software components. The software component interacts. The software component can be mapped on different ECUs. The runtime environment will abstract this complexity to you. What is important to remember is that the software component is atomic. So the software component, the single software component, is statically mapped on one ECU. You cannot partition further the single software component and deploy this and map this on different ECUs. Your application is made of multiple software components. The software components can go on different ECUs, but the single software components can go only to one ECUs. It cannot be further divided. Then, what is lying inside the software component? Well, obviously, the software component can be internally partitioned in multiple, let me say, functionalities. This is to make simpler the implementation of the single software component, but all those functionalities will run on the same ECUs. In that sense, the software component is atomic. So when dealing with software components, you have two views. You have a top-level view where you don't see what is inside the software component, you just look on the interfaces. And then you have, let me say, a bottom point of view where you can see what is inside the software component. So why is this? Well, this is done because when defining the architecture of your software, you don't care about the specific detail of the implementation of a specific software component. You just need to know what the software component shall do. You don't care how this is done. And you need to know how the service provided by the software component is delivered outside the software component. You need to know whether the software component needs to get the data, provide a function, requires a message coming from somewhere, needs to access a specific hardware driver. These are the things you are interested in. So you are interested in looking into the interfaces and the communication among software components. Well, this is made possible through the definition of the port interface of the software component. Here is where you define how the software component relates with the other software components. So this is the top level view. The bottom level view is known as software component implementation. With the implementation, you open the box and you look into the box and you define how the functionality provided by the software component is actually implemented. I'm going very fast here because I am interested in giving you a broader picture, not the single detail of this concept. So let's look into the virtual functional bus level, where we define the software architecture of our application in terms of composition of software components. Let me give you an example. The element we deal with have this shape. So we have boxes with a name, with a symbol close to the name. This is to specify which is the specific meaning of this software component. Is this something that makes some computation? Is this something that interfaces with an actuator or with a sensor? Remember that one of the functions of the AUTOSAR architecture is to give you a way for specifying software architecture. So you have to see this as a language, a platform-independent language for modeling software. Here, we are not interested in the single functionality, so this is not something that we can simulate. Here, we are interested in the architecture. So the language is defined accordingly. It can allow you to specify the purpose of the single element of the architecture, how this element interacts with the other elements, and that's it. So here, you can see that on the border of this component, we have a number of different boxes with a name and with a shape inside the boxes. This is because the AUTOSAR defines multiple ways through which the software component can interact with other software components. You have inputs that are carrying the information about the passenger being seated on the seat that is controlled by this software component. We have another input that carries the desired temperature for the seat. Then there is an information coming from the power management that tells us whether we are able to turn the heating on. And then we have other outputs, like, for example, the LED that turns on when we activate the seat heating, plus some requests towards other ECUs that provides services. So here we have a specific meaning associated with those symbols. The shape of the symbol specifies the property of the communication channel, the communication port that is set available by the software component. In general, we have, let's say, the port interface that tells us which is the specific communication protocol that has to be used by the RTE to implement the communication through that specific port. So the shape that you see on this box, on these boxes, tells which is the specific communication protocol. So, for example, this circle here means that this communication port makes use of a client-server port interface, while this other shape here, this solid triangle, means that this is a data center port interface. So basically what is important to remember here is that each software component communicates with other software components. The communication happens through communication ports. The ports are associated with a port interface, that is the communication protocol implemented by the port. And you have multiple communication protocols. You have a client-server, you have sender-receiver, and then you have other protocols that are automotive specific, like parameter interface, that allows you to access a specific constant value or calibration data. You have non-volatile data interface to access the memory services provided by the ECU. You have other advanced interfaces. So for the sake of this talk this morning, let me just focus on client-server and sender-receiver. The client-server is the interface that defines that a software component either implements a specific functionality that another software component can ask, or that the software component requires a specific functionality that another software component provides. So it is it's the same as the client server that you have, for example, in cloud computing. So you have a server that provides a service. You have multiple clients that could ask that service. While the sender-receiver is the typical example of a communication channel for data exchange. You will have a software component that provides the data, and you have multiple software components that could consume that data. As we have mentioned, we have always at least two entities that are involved in the communication. I said that we have a software component that provides a service, and we have at least one software component that requires the service. We have at least one software component that provides the data, and we have a software component that requires the data. So when defining the specific port interface for a specific software component, we also have to specify whether the software component provides the data, the service, or if the software component requires the data and the service. So that the port interface, let's say the client server, will always make the communication between two software components that makes use of the same port interface, client server, for example. One of the two will provide the service, and so we'll have a provide port of that port interface, while another one will require the service, and so we'll have a required port for that port interface. So it's quite simple. Let's imagine that the connection between two software components is like connecting a plug into a socket. So you need a plug and you need a socket. The socket is the provide port. The plug is the required port, okay? Then, if you look at the slides, you will see the enumeration of the different port types. Just a couple of examples. If we stay on the sender-receiver port interface, you will see that we have the provide port, the outgoing solid triangle, and we have the required port, ingoing solid rectangle. Similarly, for the client server, we will have the service that provides the service, and we have this circle. And then we have the client server port interface, required port. So this is the client requiring the service, and we have a half circle. Okay. What's the purpose here? Well, it's to give the designer, the architect, sorry, to the capability of expressing different possible architectures in a not ambiguous way. Being this a platform-independent language, if somebody does the modeling, the OEM, then somebody else has to do the implementation, the tier one, exchanging the model, it is clear what the OEM intended, and so the tier one can have access in a not ambiguous way to the specification of the application. So this is actually a formal language. Then being this a formal language with a specific semantic, you can make some checking. When you define your architecture, you draw a line between two software components. If the port interface is not matching, or the port type is not matching, the editor tool that you use for making the modeling can say there is a mismatch. Look into the specification because it is wrong. So this maximizes the productivity. So let's skip all of this. Let me give you an example. So let's imagine that here we are dealing with the specification of an application for the seat heater. So basically you want to have a car with some resistor on the seats so that you can, let me say, warm up the seating so that staying in the car when outside is cold is more comfortable. We may have a portion of that application that looks like this. So we have the seat heating control, that is a software component responsible for implementing the control algorithm. And then we have the seat heating software component. This arrow here means that this is a software component working as either a sensor or an actuator. So we defined our architecture dividing the functionality in two components. One is the controller and the other one is the actuator. Then the actuator, the seat heating, provides a service through a client-server port interface. As you can see, you can tell that the seat heating provides the service because here the port interface is a provide port. We have a circle. While the seat heating control requires that specific service because we have here the required port. The two are connected, meaning that the service provided by the seat heating is invoked by the seat heating control. Then here we can further refine the specification detailing which is the service. The service provided by seat heating is the operation set power. Set power receives one argument, that is the power we want to apply, and provides an output saying whether the operation has been done correctly or whether there was an error. So here we define the architecture. The client-server interface basically specifies a function call. We have the server that implements a function, the client that requires that function. What is nice is that this software component can be in the ECU, that is inside the front seat of the car, while this seating heating, another software component, can be in another ECU. You don't care about this. This is an implementation detail. For you, it is important to carry at the architecture level that the seating control ECU, software component, asks the seat heating software component to warm up the seat. Okay. Then another example is the sender-receiver. Here we have the seat heating control that decides whether to turn on and or off the heater based on the knowledge of the passenger being seated on the seat. So to save power, you just warm up the seat when somebody is seated there. So for this, we need to have a sensor software component, seat switch, that tells the seat heating control whether the passenger has been detected. So here is just a Boolean value forwarded from seat switch to seat heating control. So we have a data exchange between the two. This is happening through a sender-receiver port interface where the seat switch is the provider and the seat heating control is the requestor. And the value that is exchanged is a Boolean, passenger detected. Again, this could be a switch attached to the ECU in the seat. This could be running on an ECU in another place, and the two can be connected through the CAN network. You don't care about this. This is an implementation detail. Then, at the architecture level, you can make assembly of software components through the composition of software components. As an example, we have one instance of the heating control for the front left seat and another one for the front right seat. The two are exact instances of the same software component. They do the same job. One for the front right and the other one for the front left seats. Then we have the sensors for the, where is it? Oh, no, sorry. Then here we have the software component that gets from the user the desired temperature, that is the position, and turns on and off the LED indicating that the seat heating is active or not for that specific seat. As you can see, you can have the connections between the different software components. The connection can be one-to-one, as in this case, or can be one-to-many. The power management software component that is responsible for providing the energy for heating the seats provides the same information, seat heating, to both the software components. So this is an example of sender-receiver port interface where we have one sender and multiple receivers. Okay, then very quickly, when we are happy with the architecture, like this one, we can enter in the detail of the single software components. The software components are decomposed into runnables. You have to imagine that the runnable is a task. A task could be a cyclic task, like this one, that is invoked every given milliseconds, or the task can be an asynchronous task. A task that is invoked, it is executed when a specific event is happening. So what is important to remember here? Here it is important to understand that when we look into this level of detail, we are working inside the single software components, specifying the behavior of the software components. The behavior is implemented through multiple tasks that are called runnables. The runnables can be periodic tasks, or they can be asynchronous, aperiodic tasks. Okay? Then, runnables can be associated to communication happening on the port interfaces. For example, the software component seat heating control provides the service passenger detected, and this service is executed when a software component requires something through the port interface setting. So the inbound arrow here means that the request coming from this port, this provide port, will trigger the execution of setting, and then the other arrow here means that setting will use the value on this sender receiver. Well, what to remember here, software components are atomic, could be implemented through multiple runnables. The runnables are equivalent to software tasks scheduled by the operating system. Those tasks can be cyclic, so they are periodic tasks, or aperiodic, that are executed when operation on the communication ports are requested or invoked. Okay, then when you are happy with the specification you gave at the virtual functional bus, so you have the architecture, you are happy with the specification you gave for each software component, you can deploy this on different ECU, and so you can end up with this mapping. So we have one ECU that runs the dial and the CTD control, another ECU that runs the power management software component. They are all part of your architecture, but they are mapped on different control units. And so at the end, when you implement the software component that you mapped on the specific ECU, you have such a detailed view. So the virtual functional bus is replaced by the runtime environment that glues the port interface of the software component with the services provided by the basic software. As an example, here we have this software component that makes use of the ECU mode. Well, the counterpart of this required port will be a provide port implemented by the state manager inside the basic software. Similarly, the power management requires the data. This data is provided by somebody else. It's provided by the power management that is on a different ECU. So in order to get this data, the software component will need to make use of the communication services provided by the basic software. Last word on the methodology. You have the specification of the architecture. This is done through a dedicated editor that is producing a specific XML file. Then you have the configuration of the mapping, so you tell which software component shall go on a specific ECU, and you have the ECU description. Is another XML that gives you the definition of the properties of each ECU that you have in your architecture. The deployment tool will take care of taking the software components that are mapped on a specific ECU, will generate the RTE to connect the software component, with the needed services of the basic software, will generate the code, and will provide multiple binary codes for the different ECU where you mapped your software. All these steps must be enforced by editing tools, by authoring tools. Otherwise, the complexity of doing all this operation by hand is almost unmanageable for complex software architectures. Okay, I gave you a very broad view of what AUTOSAR is. Obviously, this is not exhaustive as presentation because we haven't addressed in detail the multiple aspects that are related to this architecture. But anyway, this was intended for you as an introduction to give you some basic concepts that you may have to, let me say, address more in detail if by chance you enter in the industry and you have to deal with AUTOSAR. Do you have any doubt, question that you want to discuss? Is there anything that I have to repeat? Okay, so we can close here. Remember to come on Friday. We have this space coming for us, so it is worth attending the presentation. Thank you.